Hey, this is Sam Dabley, and you're watching my Physics 2 Lab 6 Magnetic Braking with Faraday. So, a brief introduction. In this lab, a bar magnet is going to be released to fall down an aluminum tube that is constructed. The purpose of doing this is to study the data from the model of the bar magnet falling through the tube and to compare those results with the computational model that is created. So, this lab is going to showcase the Biot-Savart law, Faraday's law, as well as Newton's laws of motion. So, quick results and data preview. The system is the bar magnet, and the surroundings is everything else. The experimental model was used with the aluminum tube and bar magnet, and the computational model was created using GlowScript. And a quick results preview: the experimental time was found to be 1.034 seconds, and the computational time was 3.856 seconds. And the fundamental physics principles. So we have the Biot-Savart law, which says that the equation that describes the magnetic field that is generated by a constant electric current is this equation here. And Faraday's law, that an electromotive force is produced when a changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux. And you can see that right here. And we have Newton's second and third law, which say the net force is equal to the change in the system's momentum over change in time, and that for every force, there's an equal and opposite reaction force. So the experiment. For this experiment, one person in the group held the tube and magnet and then dropped the magnet so it would fall through the tube and in through the tube and out the other end. And here you can see a picture of my partner doing this while I was filming him. And here's a diagram of the experiment of the magnetic force and the net force and force of gravity. And another partner, which was me, would time the experiment and record the changes in time from when the tube entered, or when the magnet entered the tube versus when it exited the tube. And the induced currents in the tube create an upward magnetic force while the magnet is falling, causing a slow descent through the tube. So the results of the experiment. Here are some initial conditions of the tube, or initial measurements, I should say. And here is the time results, delta t, that I measured for each experiment. And here's the average time that I found. And now we get to the computational model. So here I edited the geometry of the tube line, or edited the lines of the geometry of the tube to match my specific tube. And here I edited the properties of the magnet. And then down here I edited the code in step 2 to create a function to calculate the magnetic field of the bar magnet. And then I edited step 3 to calculate the magnetic flux of the bar magnet down here. And continuing on with the code, I changed the force of gravity vector to represent gravity here. And I set ring current to be negative change in flux over ring radius here. And then I edited steps 5 and 6 to calculate the B field at each ring as the magnet falls down here. And I edited down here the net force to be gravity plus the magnetic force, and then I updated the bar velocity and bar position. And here's the results of the computational model. And here you can see the velocity versus time graph, and this large plateau in the middle is where the force of gravity is equal to the force of the magnetic induced field. So some assumptions and errors. Assume that the bar magnet acts as a magnetic dipole, as well as that air resistance is negligible, and that only two forces are at play, and that would be gravity and the magnetic force. Some errors, mainly human error in measurement, as well as friction and air resistance also being factors. So some observation statements. Which colors correspond to clockwise and counterclockwise current? Using Lenz's law, blue corresponds to clockwise and red to counterclockwise. And that could be seen here in this model. What would happen if you flip the magnet? Well, the current directions would flip. How does the real-world delta t compare with the computational one? In this experiment, I found the real-world time to be shorter than the computational time, which I assume this is due to an error in measurement. What does the plot shape tell about forces acting on the magnet? Well, the force of gravity is greater than the magnetic force at the entrance and exit of the tube, but both forces are equal within the tube. So the discussion questions. What if the resistivity of the conductor were reduced as close to zero as possible? And how would this change the dynamics of the falling magnet? Well, the magnet would be even slower, as decreasing the resistance would increase the induced current via Ohm's law, which would create a stronger opposing magnetic field. And then the second question is, what if holes and slots were cut into the tube? How would this affect the ring currents in your model? This would generate a weaker magnetic field opposing the force of gravity, and that would be due to less current rings, so the magnet would fall faster. Thank you for watching. I hope you learned something, and have a good one.